Okay. Hello, everyone. As you have noticed, this classroom is not big enough, so I'll try to move. We'll have to move around. But welcome to the course, Logic in Computer Science. This is a course for the interdisciplinary students of computer science and math, just to get a feel for it. Who here is ISRM? And who's math? And who's Erasmus? Hello. Okay. So we are going to do this course in a slightly different way than the last time around when it was given by Professor Simpson. He sort of covered many topics to give some overview of the area, and we are instead going to try something different, and we'll focus more on a particular topic. Let me just pull up the pages here. Where are the pages? The pages are here. There are the pages. Okay. So I've set up some resources here. Let me show you first the resources, and then I can tell you what the course requirements are and stuff like that. Okay, so you should all be familiar with split naučilnica. So in particular, if you are an exchange student, then if anything of what I'm saying is unclear, you have to come to me and say, I don't know what that was, okay? So then in here somewhere there is a course called, so the math students, you found it, right? Because it's classified under ISRM, because the math students, for you, this is an elective. So you have to find this course, Logic in Computer Science. And then there's some stuff here, and you can read all of this. And then there are course notes, which are, so let's see, what are these things? Okay, news forum, this is going to be used if we have an announcement that we want to make and we want it archived better than the Discord. There are two exercise classes, which has a capacity of 15, so obviously we have a problem. So that's another problem that we will try to solve until before tomorrow at 10 o'clock. Okay, that's an interesting problem to solve. You saw Danielle. We have a Discord server. Okay, so that's going to be useful. It's probably the best way to just immediately get attention. And if you have a question, you get stuck on something, just talk there. Then there is a repository on GitHub. Yes, okay. So we're going to use GitHub and Git quite heavily to distribute materials. You will work on your projects using GitHub. So if you're not familiar with GitHub, that's another reason why you want to come to me and say, I'm not familiar with Git and GitHub, please help. There is a repository here that Danielle has set up where all the exercises will be. And so far he has exercises for tomorrow. And there are fairly extensive installation instructions here for Agda, because we will be starting with Agda. And everybody should fork and I think it's probably best, yes, you should definitely fork this. So you go here, fork, you make a copy for yourself. I already made a copy for myself, so you click here. I can't do it again because I already did. And then you see here, then you get your own copy of this, and this is what you can then work with. It's the easiest. And you can then get it to your computer. Let me just do this. I will use the command line. You don't have to. So you get a copy of the repository on your computer. And I already made a mistake, I think, because I was supposed to use this repository also pulls in the Agda standard library. So how to get course materials? You have to use recurse submodules. Okay, so this is the thing I want. Well, I can just put it here. there are instructions on what to do if you forgot this. And now it's going to pull in all of Agda standard library, and this is definitely something that you should do and know how to do it, because this is how you will use your repository. Now it's taking forever. Then we have, where were we? Okay, we have the Discord server that you should join. We said that. And then we have lecture notes, and then there will be recordings. I am recording. You can always check whether I'm recording. You see this dot? This means I'm recording. So if you see that this dot is missing, please tell me that I'm not recording, okay? And the videos will appear here, but there are no videos yet, of course. So then we have the lecture notes, which is the same thing as this, except it's local on my computer, where the material for the first part of the course, at least, is going to be collected. So this has, so let's just go through this intro, just so, because then I know I won't forget to say certain things. So we are going to use, at the beginning at least, Agda. Agda is a proof assistant and or programming language, depending on how you want to take your point of view. And Agda is used through an editor, and there are two editors that definitely support Agda. I think there might be some Vim business going on, so if we have any Vim people here, you're on your own, I'm sorry. So Visual Studio Code is probably what most people here have been using, and if you're old, then you can use Emacs, yes? And both have fairly good support for Agda, and this is something that is in these instructions that I showed you on the repository that Daniel wrote up on how to get these things going, and how to install Agda. And it's particularly easy if you go through Visual Studio Code, because you might have Visual Studio Code. I hope many of you do. And then you install the Agda package, and then the Agda package can install Agda, so you don't have to, you're done after that point. Okay, so this course, as I usually like to do when possible, and especially with master's level courses, I like courses to be project-based. That is to say, you are going to work on your own project, since there are, yep, no, come in. They'll give you a chair. You can sit on a table or the desk or somewhere. But is there a free chair? No? Bring a chair. So the course will be completed by working on a class project. Since there is a lot of you, we'll probably form groups, because it's going to be impossible for Daniel and me to oversee such a huge number of projects, but also working in a team can be a very good learning experience. I would opt for teams of size 2, I think, because experience shows that when you have size 3, the group dynamics becomes chaotic. Find a place. Okay, so, but we don't have to talk about this now, this will come later, but the point is that a good part of this course will be devoted to project work. So, for instance, instead of having regular lab exercises, we are going to say, you're working on the project, we don't have regular exercises, but you can come to the lab, and if you have a question, or if you just want company or somebody to look at what you're doing, come and work on the project. Okay, so that's the second half of the second half of the course is going to be like that. The first half we have to learn things, so we're going to do it the traditional way with lectures and everything. But then it'll become more and more project-oriented, and I would hope that everybody, or practically everybody, will be done by the end of the classes. That is to say, end of May, you should actually have your grade. I don't want to drag this into the exam period, because you probably have better things to do in the exam period than to write code in Agda. So that's how we're going to try to organize things. But this also means you can't just randomly not work on your project for 2 months. That's not going to be good, right? So we'll make you report, and we'll see your project progress, because we will spy on your Git repository. Okay, so lectures are in this room. Hopefully, this is the only time that we're in this room. And then we need to do something about this stuff also. So we have some non-solvable problems to solve. The course material, of course, is okay. So this I already showed you. This is the official page in the Moodle online thing. Then there is the repository, which I already showed you that you should fork. Just click fork. You get your own copy. Work with that copy, and then you can pull in the changes as they come. Video recordings. I did this. Course repository. Yes, course repository. This is the same thing as this. Okay. So obviously I need to improve these notes. There are two sources of reading material about Agda that I highly recommend, and we're going to draw from them also heavily. And in fact, these lectures were inspired by them. So the first one is Programming Language Foundations in Agda by Phil Wadler. And in particular, part 1 is the one that we will be taking a close look at, which has sort of the basics of type theory and Agda and stuff like that and how you work with it. And then it goes more into programming language theory. So that's the sort of thing that ISRM students know under theory of programming languages. You have a course, right? And in fact, it's this semester. Okay. So in fact, if somebody is interested in doing this sort of thing, formalizing theory of programming languages, we can probably find some courses. I mean, we will find some courses in that direction. So keep that in mind. And if you are and to find out whether you're interested, one way to do this is to read parts 2 and 3 and see what's in them to see whether that's the sort of thing that you like. So it's mathematical theory of programming languages. And then the other one, which is more mathematical in nature, is Introduction to Univalent Foundations of Mathematics with Agda. This is by my good colleague Martin Escarda from Birmingham. And this is written in Agda, and there's a lot of it. I mean, there's a lot of the other one as well, but this one is in one file, so it's scarier. Just a second. I have to take this away. Okay. So here I will give specific links, but again, it's this stuff at the beginning, like the type of natural numbers, and you can just find, I think you will find this resource also useful, also because you will see how things can be approached from different directions. This one is more mathematical, the other one is more a programming point of view, but not really. I mean, it's also quite heavy on I mean, it's also quite careful about properly explaining theory and so on. So these are the two main courses, and I recommend reading these sources. Then, of course, there's Agda documentation, which is here, which is surprisingly short. You can actually read all of this without going crazy. Then there's the Agda standard library, which we will use because we don't want to reinvent the wheel. There's some stuff in here. These are just the modules. Okay, and each module has stuff in it. Yeah, okay. So this, I advise you not to try to read all of it. Then we have a brand new proof assistance Stack Exchange site. So this is a good place to peek. It's brand new, so it doesn't have a lot of material. But if you are going to participate, please behave nicely, because they'll find out you're my students. Okay, so GitHub resources. There are lots of GitHub resources. I think the people who are not familiar with GitHub, it's better if you just come to me and say GitHub. Here are some other possible pieces of software that some of the projects will be based on. So if there are people who are interested in formalizing mathematics, it can be done in Agda, but lately there has also been a lot of movement in formalization with a different proof assistant called Lean, and it has a very strong community that's very active, and so this is also a good tool to try out. I didn't list everything. There is Coq, for instance. That's also a proof assistant that's very powerful and is a very good tool. So that's another opportunity. And our own Daniel is an expert on this particular thing, which is, I think, also very nice to learn, which is F* is a language which is like, it's a bit like OCaml, but it comes with very strong support for proving correctness of your programs. So now after this, if I had to describe to you what are we going to do is, I would say it like this. We're at first going to learn the basics of type theory and how to use a proof assistant, and later on other tools that are like a bit like proof assistants, but they all focus on some aspect of formalization. That is to say, ways of checking with the computer that your proofs are correct, that your programs are correct, maybe developing some mathematical structures, and all the time with the aid of a computer that is helping you, or it thinks it's helping you, but you really hate it. But it's definitely verifying all your steps, so you can't do anything that is invalid. And I think these tools will become more and more important in the future. They are already quite important in some areas of computer science, for instance, in software verification, when you have to verify that software works correctly, or you have to verify that maybe a communication protocol or a security protocol. There are occasions where it's actually worth verifying that these things work correctly. There aren't many of those occasions, but if you're faced with one of them, it's good to have this knowledge. Moreover, if you see these sorts of techniques, which I think show a little bit what the future of programming is going to look like, I think in general things are going to go in the direction of having ever better support, not just for typing code, but also for analyzing code and maybe providing useful help when you're programming. So that's the techniques, the technology that we're learning. The tools are in fairly early stages, so these are tools that have come out of academia. Lean is actually developed by Microsoft Research, so it's not straight out of academia, but nonetheless, the tools like this are sort of at the forefront of trying out what can be done. There are lots of industrial tools that are also similar, older maybe and powerful, and learning this I think is just very good if you are ever going to be serious about software. If you're a mathematician, then this I think is also important, because I think it stands to reason that mathematics is not always going to be done the way it's been done since the Middle Ages, which is like some smart person writing pieces of, like, scribbling something on paper, right? It has to move forward, and computer science is going to come and it's going to turn mathematics on its head, just like it has done with everything else. I think it would be completely unrealistic to think that it is not going to do that. Now, I don't know if the proof assistants are the thing that's going to turn mathematics on its head. Maybe it's going to be some stupid neural network that Google will come up with, who knows? But this is one of my better bets that it's going to be like that. So that's maybe motivation for mathematicians, why you should be in this course. Okay, enough of that. That's just the general stuff. Let's get going. I would strongly suggest that as your home exercise, you follow the instructions that Danielle has prepared in that Git repository, and you get Agda working on your computer. If by any chance you do not have your own computer, you should definitely come to me, okay? Because then we will need to also try to solve that problem. So if possible, please try to do that before tomorrow's exercises. The software on the computer lab, we have Agda and Visual Studio Code installed there, but it's kind of flaky. And it's ridiculous. I warned you, it's academic software. So for instance, you can't open an Agda file on a network file system. You just can't. It dies. So if you work on computers tomorrow, you will be working out of ctemp. That's not a good thing to do, but that's what you will be doing. So I would recommend that people bring, if you can, if it's not too much trouble, bring your laptop, okay? With the software working, I think your life will be a lot easier if you do that. You can, of course, use the computer labs. They have Agda installed, but consider yourself warned, okay? You're going to lose more nerves trying to work with that. Also, it seems like since we have a problem with the number of people, and it may not be solved by tomorrow, that's another reason why you should be bringing your laptop tomorrow. I don't know. Maybe the classroom will take place in the benches over there outside 312. Who knows? Okay. Okay, installing and obtaining Agda. See what the instructions say. If the instructions are confusing, not working, your computer is emitting smoke, please ask on Discord. We'll try to solve it. As far as Agda is concerned, so it's a proof assistant. What is a proof assistant? Okay, so a proof assistant is so what's a computer? A computer used to be a person that computed. But then, nowadays, a computer is a machine that computes. So it helps people compute with numbers. Well, more nowadays than just numbers, but that's how it got started. And a proof assistant is simply somebody or something that assists you with proofs. But you have to understand proofs here in a very broad way. It could also be constructions, not just proofs. Like, maybe you're constructing a complicated mathematical object. Maybe you're constructing some fancy data structure. That's also something that proof assistants do. So we're just going to start using Agda because I think that's the best way to see how things work. Why Agda? Why not some of the others? Agda, so I've heard it said, I don't know who it was, but it was somebody at some beer after a conference said that Agda is like the Porsche of proof assistants. It's slick and it's fast and you can crash. But Coq is like a truck, you see? So when you don't know how to use Coq, then it's not your fault. It's complicated. It's really complex, big. You know it can do everything. You just don't know how to do it. In Agda, you just sit down. There's the wheel. There's the pedal, and you go vroom. Yeah. And so it's much more direct in the style. It doesn't hide anything. You do everything directly. And I think this is a good beginning. But I think a lot of you might switch to a different proof assistant afterwards, where you will get more help from the proof assistant. Because it offers more help, it's usually also more complex to use, because you now have to know how to ask for help. You can't just write help. Okay, so every Agda file is in an Agda .agda file. There is also a literate mode called LAgda, but let me not get into that now. And every Agda file has to contain a module. So an Agda development contains a bunch of modules, and the module has to have the same name as the file. In fact, this thing here, I will open it in Emacs in a moment. By the way, I will be using Emacs, right? I'm qualified to use Emacs. So you can use Visual Studio Code, of course. So every Agda file starts, it can have some import statements, but it starts with module, okay? And so since this is the name of the file where we can find the module, it's declared here. I will show you in a moment how this works, the literate stuff. The literate stuff just means that Agda code is interspersed inside some text, and Agda says, okay, let me just ignore all the text and let me evaluate the code. So I will now switch to the file because this will be better. Where's my Emacs? There it is. Okay. Oh, I'll probably have to repeat this. Yep. So this is the same thing that we were just looking at in Markdown mode, and I'm using Jupyter Book to convert it to the HTML. We've been here before. Okay. So any Agda code is in code blocks, which are these triple backquote thingies. So anything that is between triple backquotes is actually Agda code. And I'm in Markdown mode, so let me switch to Agda mode. There we go. Okay, so now the Agda is ignoring all the white stuff, and it's the colored things are actual Agda code. Okay, so as I already said, you always have to start with the module, which is the same as the name of the file, and then you put the rest in. So let's have a look at a definition in Agda. So this is the definition of the Booleans. When you start up Agda, there is almost nothing in it. You don't have natural numbers. You don't have Booleans. There are very few predefined things. You can find them in the standard library, but you have to explicitly use the standard library. It's not just there. You have to say, I want to use it. It comes as a clean slate, and then you can define whatever you want. And it offers some support, as we will see, of course, or you can use the standard library. Anyhow, here's how you define a data type of Booleans. You say, well, I have a data type, and then you name the data type, and it says it's going to be a set. Now, this set business is a bit of a misnomer because it can mean one of two things. It can mean a type, but it can also mean a logical statement. But it's called set, okay? This is maybe a little bit for historic reasons, so please don't pay too much attention to this. But also it's good to just say, okay, yeah, we defined a set. And then down here, you have constructors. You say, what are the elements of my set? And you say, well, false and true are the elements of this set. And now Agda knows that we have a type. I'll call it a type. We have the type bool, which has two elements called false and true. If there are any questions, you should just ask, stop me. Okay? This I think I've said. Okay, there are remarks like this see also here, that in fact there are universes of sets, a whole hierarchy, and we will deal with that later, but we're not going to do that now. But sometimes I have these references where you can read more about a particular topic, and these topics are usually interesting. I try not to point to boring topics. Anyhow, so here's how you define a thing. So when you define, so by the way, this is the Slovene word for truth. Okay, so. And this is how you make comments. So you say, I'm going to define some constant or a name, and then you say what its type is, and then you give the definition. Okay, that's all. You will see shortly how we work with Agda, but let's just see another one. So here's another one. Suppose you want to define logical conjunction. Then we say we're going to define and it's going to take a Boolean and another Boolean, and it'll take a Boolean. Now this should be familiar if you've ever done any functional programming. So who has done Camel? Who has done Haskell? Okay, who's done any kind of functional programming? You know, almost okay. So it's going to be helpful if you have a little bit of experience with functional programming. Otherwise, you will just learn functional programming as a subset of Agda, really. So this means we have a function. We're going to have a function. This function takes a Boolean, and it returns a function. So it's really then this function wants another Boolean, which then returns a Boolean. The way you read this in practice is you just say, I have a function of two arguments. It takes two Booleans. Okay, and then you can have definition by cases like this. And Agda is very good at figuring out what the cases need to be, whether you have included all the cases, and stuff like that. And in fact, Agda has something very, very cool, which is interactive mode. Proof assistants are interactive, so they help you do the thing you want to do. So now I'm going to show you how this is actually programmed. So the way that you program this is you say, you type this much, and they say, okay, I need to define and. So I say, okay, I'm going to have P and Q, and then I need to produce the result. But I don't know what the result is, so I'll just put in a question mark. And then I tell Agda, please have a look at the file. And this is Control-C, Control-L. Keycaster. There we go. I installed this little gadget. Just so. What do I need to do? In the dock, tralala, show preferences, general display. I think it's set up properly. This is gone. It's not gone, is it? Yeah, it's gone. Is it showing up? I was going to, okay, I could also do this later on the video. I was going to have the keystrokes displayed. Why are they not being displayed? Oh, of course, I know why. I upgraded to Monterey yesterday. Surely something's got to break. So it seems like this one did. Let's try again. Default, select visualizer, general, in the dock. Hey, how about here? Okay. Stop casting. It should be working. Does anybody see anything? No, I don't. Okay. Okay, so I press Control-C, Control-L, and the keystrokes are the same on Visual Studio Code and Emacs. So Control-C, Control-L is going to load the file. So I say, load the file. And Agda says, hey, you had a question mark there. What do you want to do about it? And this is called a hole. So now I have a hole that I need to fill. Okay? So I can do a number of things. I could give the result and press Control-C space. And, oh, down here, see? Ah, they're appearing down here in the corner. Okay, for the video people, in the lower right, you can see what I'm typing. Okay, so you can put in something, and then it'll tell you whether it's okay. So let's repeat. So what if I say something idiotic like this? Bool is not a Boolean value, it's a type, or set, that's even worse. And I say, please accept this. And it says, no, I'm not accepting this. Okay? So these holes are super useful, and that's how you write code in Agda. That is how you interactively write code. You have a hole that you need to fill, and there are many things you can do with the hole. You can give an answer. You can say, I actually want to split into different cases. Please, I want to consider several cases. And then Agda will tell you what the cases are. Or you can also refine, which means you change the hole to some sub-problem. You make a little bit of progress, but you don't give it the final result yet. So we're going to see all of this. So let me just do things the way I would do here. So I would say, I need to consider cases depending on P. So this is Control-C, Control-C. So I say Control-C, Control-C, and it says, okay, you want to consider cases on what? And I say, I want to consider cases on P. And now it says, okay, I know that P is false or true, so here are the two cases for you to consider. So now I press Control-C, Control-F to go forward to the first hole, and I say, what's the result? What's the result of AND, false, and Q? Well, now I have possibilities. I could immediately say false, right? The conjunction of false and anything is false. Or I could say I also want to consider cases on Q. By the way, I can also put Q in the hole and say Control-C, Control-C, and then that will tell Agda, the thing that I put in the hole, that's what I want my cases on. And that's how I usually say. So I say, I want to split cases on Q. Control-C, Control-C, boom. And now I put in answers. This one is false, Control-C space. Oh, it's happy. Control-C F for forward. This one is still false. Control-C space. It accepted. Control-C forward. What's the result? I could split cases again, or I could just say Q. There are several possible definitions. But that is how you write code in Agda. Yes? You work interactively with holes. So, there are videos and stuff on how to work interactively, but really you will learn by working in the exercises. Here are some basic bindings that you might find useful, which are also listed in the documentation and everywhere else. So here I have a different definition of bool, which is the one that is more optimized, right? We noticed from the beginning that we could do better. So again, you would say, this much I have to type, okay? I say, I want that type, I want this stuff here, and then I press Control-C, Control-L to load, and I say, split on P, Control-C-C. Oh, I know the answer, it's false, Control-C space, and then I say, here it's Q, and I'm done. Actually, since you don't need Q here, see this Q, that you don't have to mention it on the other side, you can use underscore, which means anonymous pattern. It means whatever is here, I'm not interested. I'm not naming it. It can be whatever. I don't need this name. So that's a third version of Boolean AND. Okay? So here's an example of how you would do negation. So again, this is going to quickly get boring, but you would do it like this. You type this, Control-C, Control-L. I say, please split on C, and I type in this one is true, and this one is false. Okay? Now, let's try doing something slightly more interesting. Agda has very good support for the UTF-8 characters. In fact, this is used all the time in Agda, and it's used in ways that might surprise you at times. People have, in combination with the mixfix notation, which we're going to explain shortly, people have devised ways of making Agda code look quite nice sometimes. So for instance, it's kind of stupid that you have to put not here. How about if we use the negation symbol? Now, first of all, how do you type the negation symbol? You type them by using LaTeX codes. So \not. No, \neg is not. Yes? I don't know, O+, \integral, \alpha, \big gamma, V dash. It's got a bunch of things. You can also just draw arrows. Okay, so like draw an arrow. It's always / and then something. You want a ridiculously looking semicolon. Here's a ridiculously looking semicolon. And sometimes you have to choose the right one, so maybe I'll pick, which one is best here? None. Okay, I'll have a ridiculously looking colon, I think is better. Anyway, there's lots of this here. How about this one? Okay. So UTF support is good. So how do I type this? Let me start from scratch here. So I would say I want to define negation, which is \neg. It's going to go from bool. And now how do I draw the arrow? I just say 2 bool. This is \2 neg of p equals ? And now I repeat the same thing as before. Split. This one is true. This one is false. Okay, so that's going to be helpful. Now, of course, the next thing you would want is you would also want this conjunction here to be nice so that it looks like logical AND. How do you do that? For that, we have to learn about mixfix syntax. So here, this is better. Here. When you work with operators, where is my note? Okay, so I can see this. When you work with operators, you kind of have several possibilities. A thing like plus is infix. Why is it infix? It's infix because it stands between two things. A thing like what is a good prefix one? Something that stands in front. Well, negation, of course. Okay, is prefix because it's an operator that stands in front of its argument. And then you can also have postfix, which would be something like factorial, because it stands behind, after the argument. But then there are also weird possibilities, like, for instance, something like if then else. You want to write it, you don't want to write if then else like this. If then else, and then PAB. That's not very nice. You want to write it like this. If P, then A, else B. And this is called, in general, mixfix, because it's mixing notations. So sometimes you want to have an operator which is made of many parts, and then write things in whatever way you want. So another example would be, for instance, when you have indexing into an array. If this is an array, and I want to have the ith index, I would write it like this. So this is just saying that I have a mixfix operator. What does this operator look like? Well, it has one spot here for A, then it has this, then it has another spot here for this, and then it has that. And this is how you explain to Agda how you're going to use your operator. You have an operator, and you just put underscores where you want the arguments to go. So for instance, if you want to define logical conjunction, you define this. And Agda will say, oh yes, this underscore means that you want your first argument here, and this underscore means you want your second argument here, so we're going to write things like that. There are two other things that we need to mention here. One is that operators have priority. So, for instance, we want something like this. We want this to be understood this way, right? So that means that this one has to have a higher priority than that one. That's something that we want to be able to use as well. so that we don't have to put parentheses on all the time. And there is a third feature, which is if I have some random operator, I don't know, this, then if I repeat it like this, there are two options. One option is that we understand when we see this, we say, this is what was meant, and this means that it is left associative. This is called left associativity. This has nothing to do with associativity in algebra. This has to do with how do I understand this operation. Do I understand the parentheses to be implicitly this way or the other way? The other way, is of course like that. And in that case, it's called right associativity. And we'll see examples of all of them. And you can have no associativity, in which case, if you don't know whether, if there is no agreement on whether it's left or right, then this is just non-associative. And it's in fact ambiguous. Let's say I know how to spell ambiguous. Okay, so, and then you shouldn't use this. You have to put in the parentheses, otherwise people don't know what you mean. Okay, Agda supports all of what I just said. Yes? So let's see how. So, when you have a name like this, you can declare it, and you can declare its precedence. Higher means more tight. So multiplication should have a higher number than addition. And then this L means left associative. This L stands for left associative. If I put a right here, it will be right associative. If I do nothing, it won't be associative. So it's left. I want to say it's left associative with precedence 10, and here it is. And then I define it. And I define it just like before, but now you see I can immediately use the infix notation here. I'm just already using it as an operator because that's how Agda understands this. I could also do this, but there is no need. What is this? Wedge? Something weird like that? I could write it like this if I wanted to. But you see, Agda already, as soon as Agda said, no, infix, please don't do that. Formally, you can write it as a normal operator, but Agda really wants you to just do the right thing. What was this? It was this, right? This was Q. Okay, and we didn't need this one. Okay, so we will use this a lot. We'll use this a lot. So here's another example. How would we do if then else? Okay, so here's if then else. So suppose you want to have nice notation for if then else. You say, well, I'm going to define if then else, and you just put underscores somewhere. Like here's going to be one argument, here's going to be the second one, here's going to be the third one, and you define it. Here we see something more complicated than what we had so far, so we need to explain this. But observe first how this is defined. I just write if then else just like I normally would. No special deal. This is a syntax introduced by the user. So that's how Agda works in general. Okay, so what is this business here? The way you read this is, the first argument is a set. The second argument is a Boolean. The third argument is an element of A. The fourth argument is an element of A, and the result is going to be an A. But then if you count the arguments here, there are 3. 1, 2, 3. But here, there are 4. This is because this one is in curly braces. Curly braces mean implicit argument. So implicit argument means it's an argument, but we're not going to write it down. We'll just leave it out. And then Agda will have to compute what that argument is supposed to be. How will it compute that? Well, it will compute it because it will look at the type of X and will say, aha, I know that the type of X has to be A, so I know what A is. It will also compare it with the type of Y and it will complain if they are not the same because it should be A twice here. Okay? So Agda is very good at computing these sorts of things and is very helpful because then you don't have to explain everything. This is where the word assistant comes in. Yes? It takes a little bit of practice to know when to put the curly braces in and when not to put the curly braces in. But here's a good rule of thumb. if this A, if a type appears somewhere later on, then Agda will be able to tell what it is. So you could put it in the curly braces. And we will use this strategy in general. And here is how we define if then else. We say, well, if the condition is false, okay, maybe I should do this like this. Otherwise I will confuse everybody. Okay, if it is false, then the result is the else part. And if it's true, the result is the then part. And I will actually probably do this. Let's see what Agda thinks is the correct way. If P, then X else Y equals question mark. Split on P. It wants false first. Okay.
Because you wrote false.
Yes, it's probably because I wrote false here in this order. If I change the order here, then of course it'll want the other order everywhere. This would, yes?
So these curly braces are just a form to introduce type polymorphism.
This is, no, so the question is whether this is about type polymorphism. Yeah. Okay, so first of all, type polymorphism means that you have a function which takes arguments of an arbitrary type. Type polymorphism is something that exists, say, in Haskell and OCaml. In a sense, it's a special case of what Agda can do, because Agda doesn't think of this, it's not really polymorphism. What it really is, it's a function which just takes a set as an argument. But it is a named argument. You see, we say the first argument is set, and we are naming it A because we are going to use it in the rest of the type. We're going to call it something. We will see a lot of this, you will get used to it. So the way you read this is, the first argument is a set called A. The second argument is bool. It's not named, but I could name it if I wanted to. I could put a name here. I'll say, okay, yeah, sure, you called it P, but I don't have to do that because I never used it later on. But I have to name A because I want to say, and here we're going to have something of type A. So this is far more general than the polymorphism that you see in OCaml or Haskell. Okay, so these are the implicit arguments. There's some pointers on implicit arguments where you can read. Okay, so it's also worthwhile actually reading the mixfix operator stuff. Okay, and then okay, what else? The implicit argument documentation is also here. And we will use this, we'll just learn this through osmosis. So this is a good stopping point. We can stop here and have a break. And I suggest that we move to, let me just make sure, we're just going to possess it. I'm not even going to try to reserve it. Let's hope nobody had the same idea. So if I'm reading this correctly, we should be able to go into 205. So let's all move to 205. If we can't, everybody will have to come back. So it'll be a race for the good seats. Implicit arguments. There's one other thing that I can show you, namely that if you do need or want an implicit argument, you can get your hands on it. It doesn't have to be left out. So the typical example is the identity function. So with the identity function, you want to define id of x equals x. Now, first of all, let me show you that if it's not implicit, okay, then you have to define it like this. Because now, now everything else is broken because I broke id. But if I make this an explicit argument, then I have to write it here. Okay, I hope that would be obvious. And this is how you name an argument. So this is now an argument named A. If I make it implicit, then I don't have to name it. I don't have to mention it. I just leave it out, and it all works. By the way, you could also have some unnecessary implicit arguments that are not used, but in that case, you start getting into trouble because Agda can't tell what this banana is going to be. See, when I define id here, this is colored in a weird way. Okay, this is the dreaded yellow. So that means Agda says, well, some of these implicit arguments, I have no idea what they are. And so it's coloring things in suspicious ways, and this is one way to get into trouble. So on arguments, these two are problematic because they're not used anywhere else, and so there will be no information about them. And so Agda will not be able to tell what they're supposed to be. So here's how you define, this is how you use the identity function. You just apply it to something and you get whatever you get. By the way, you can also compute. I mentioned that Agda is also a programming language. So if I press Control-C, Control-N, then it's asking me, what would you like to compute? And I say, please compute e.false. And it computes false. I can also compute, say, compute true and false. And it says, well, it says false. So now you can't tell whether it's still the same false. So let's try true, and true is true. Okay, so down here I have the response window. If I really, really want to specify A, I may by simply putting it in the curly braces, and then it just means, yep, this argument here that was left out, it's actually supposed to be bool. And this can sometimes be useful, and sometimes it is necessary. You can also do it like this. You name it. You say, I want the argument A, the implicit argument A, I want it to be bool. Warning, this is not what you think it is. This says that false has type A equal bool. A equal bool is a valid variable name in Agda. Almost anything without spaces is a valid variable name. It's happy. It says, yep, we defined A equals bool, and we're going to use this stuff a lot. And we're going to have really weird names. And we will do that all the time. So none of this boring, do we use camel toe or do we use underscores? Well, you don't use underscores, first of all, because they have a special meaning. If you do anything, if you want to have multi-words, you usually use the minus sign. Okay, let's do something real. Let's also define the natural type, the type of natural numbers. Okay, so here's how you would do it. You would say, I'm going to define natural numbers, and this is the pretty blackboard n, which you get by typing little bn, little ba, little b, little a, little b x. Okay. Ooh, wow. Okay, interesting. So lots of things you can define. So we're going to define the natural numbers, and this one is, again, there are two constructors, and one is 0, and I write it with the word 0. There's a reason why I'm not using the number, and we'll come to that later. And then I have successor, which under normal circumstances, personally, I would write like this, just so that they're both 4 letters. But for some reason, the standard library uses successor with a single C, so just to be compatible with that, we're going to use a single C here. And then, if you want to define number 1, well, you say number 1 is the successor of 0. You can also define number 10 here. But this is not terribly interesting. These are numbers in the unary system. That's not good. So, Agda has some built-in support for certain things, and one of them is the natural numbers. So, this here, this is like a magic spell, okay? So it's called it's not called a magic spell. It's called a pragma, but think of it as black magic. When you use this, if you disappear in a puff of smoke, it's your fault, okay? So this says, I want built-in support for the natural numbers for the type n. So first you define your own natural numbers. You get to choose what you call the successor and the 0. And Agda will look at this and will say, yeah, this fits the definition of natural numbers. So I could say here, banana. Well, I would break this stuff here, but I wouldn't break the pragma. The pragma would figure out, yep, the successor. So with that, once you execute this, now it will internally represent integers in natural numbers in an efficient way. And also, it will automatically translate from my definition to the internal. And so I can now define 42 like this. I don't have to write 42 successors. In fact, I can write pretty big numbers now, and this would be undoable with successor of successor of successor. So that's not something that we would do with the other definition of natural numbers. By the way, you will also notice that here, when I define 42 or trillion, I didn't do this part. Okay? I didn't write the signature. I didn't write the type of 42. You can leave it out in a definition, but it's good practice to put it in. This is a practice similar to Haskell. In Haskell, you don't have to write the type of the thing you're defining, but everybody will think you're slightly weird if you don't do so. Whereas in OCaml, everybody will think that, well, if you do put in the types, you should at least put it in the interface file, not next to the definition. You can't really put it, or you can put it next to inside the definition. Okay, so these are different communities doing different things. Why would you want to write the type? Because if you write the type, Agda will know how to help you with the question marks. See, if I don't write the type and I say 42 is something, and I say, hey, Control-C, comma, what do you want? It says, your goal is to satisfy goal number underscore 40, because it doesn't know what I want. But if I say 42, it's going to be a natural number, and like I'm here and I say, hey, what's the goal? It'll say, the goal is to define a natural number. When you're sitting inside a hole, you can press Control-C, comma, and it'll tell you what that hole should be. It should be a natural number. So, okay, here's a natural number. We can also define recursive functions. So this is yet another thing that Agda is really good at. It knows that these are definitions of inductive data types, and I will talk about what this word inductive means. But because they are inductive, whatever that means, they support definition by recursion. And Agda allows you to have recursive definitions. So here's the definition of the function that doubles numbers. So how do you double 0? You double 0 by, well, returning 0, double of 0, 0. So multiplied by 2, right? So how do you multiply by 2 if it's successor? Well, let's calculate, well, not here, in case this is not clear. It's just this, right? So 2 times n plus 1 equals 2 times n plus 1 plus 1. So double successor. Double successor of double, and here is the recursive call. Here's an important bit. Agda is a total language. So when you define a function, it has to be completely defined, and it has to be defined everywhere. It has to terminate. You cannot define functions that don't terminate. There is an internal checker that checks for termination, which figures out that your recursive calls ensure that they will always terminate, that the recursion will always end. This termination checker is smart, but it's not perfect, because there is no perfect termination checker. If any of you have taken computability theory courses, okay, so checking for termination of a given piece of code is an undecidable statement. So there can be no perfect termination checker, but Agda is pretty good at it, and in practice there are only few occasions where this hits a problem. So, recursive functions. We can now also calculate. So, for instance, let's go double of 23 is 46. The result is down here. It's kind of in a small font. I hope you can see it. You can also define other functions. So, here's how we would define addition. We would say, let's make addition infix, left infix with precedence 6. Somebody asked me, who was it, Ivan? Somebody asked me, you ask me, these numbers, how do I choose these numbers? And as far as I can tell, people choose it kind of randomly, but not entirely randomly. If you pick the wrong numbers, then the precedences will make you write parentheses in strange places, and then you'll go back and fix them. If you don't, I can leave the number out, and then the precedence will be 20, is the default precedence. So anyhow, how do we define plus? We say we're going to define an infix operator. Here it is, infix operator. And now we need to recurse on what? Well, we will recurse on the first argument here. We say 0 plus n is n. And the successor of m plus n is the successor of m plus n. I hope you have seen these definitions, or if you have not, that you are able to process them. So the question is, why isn't this written in a tail recursive way? So the tail recursive way would mean that the last operation is a plus. Yes. Okay. So, but then you would need an accumulator, right? That does it. Oh. So, okay, so maybe I misunderstood your suggestion, so let me try it. So your suggestion was, let me comment this one out. Your suggestion was to change this to? Move the soup to the end, so it's n plus soup n. Like this? Okay, let's see. Well, that was a good suggestion, except for the fact that now the built-in support doesn't work. Let's see. 10 plus 42. 52. It works. So why is this a good suggestion? This is because the last thing that happens in this definition is the recursive call. And there is a special optimization called tail recursion. Did anybody teach you tail recursion? Some people nodding. Okay. When you have a reasonable compiler, tail recursion gets turned into a loop. So there's no recursion anymore. So that's why this is a good suggestion. I will confess that I don't know whether internally Agda actually did anything with this. It may be the case that it didn't optimize, so I don't know. But apparently, the standard definition is this one. I would venture to say that's so because Peano did it this way, or there's probably some historic reason why this one. And then similarly, we have multiplication. So multiplication, 0 times n is 0. And if you multiply successor of m and n, you multiply m and n and then plus n. Okay? And you can have built-in support for these. You can say, please use built-in addition and multiplication. This built-in support is there in case you really want to calculate with natural numbers, or you don't want to be embarrassed in front of your friends, because then you say, well, but your Agda is stupid. It can't even calculate 1,000 times 2,000 because it's in unary. This is ridiculous. And they would have a point, right? But like this, sure, right? Apparently, it's not using the unary because this would be crazy, okay? Any questions here? Okay, so let's now stop and think a little bit about what was going on. And for that, it's better to look at this page here. Nope. This page here. And this is this idea of inductive generation. So, very often in mathematics, computer science, we have constructions which have a particular shape, a particular form that is called inductive. Inductive means that there are some basic rules or constructions that tell you how to make one basic step or how to make another thing from the previously existing things. And then you consider the totality of all the things generated by these constructions. So we already saw natural numbers. Natural numbers are like that. Inductive constructions are described in logic and foundations and in type theory using what is normally called inference rule. So an inference rule looks like this, or just a rule. Actually, probably the better way to call this is it's an inductive rule. You have some stuff at the top. This is just the way we write them. And these are called hypotheses or premises. I prefer premises. And then down here you have something that's called the conclusion. And the way you read this is you say, if I have these things above the line, all of them, then I can get this thing below the line. Yes? And for instance, you could describe the construction of natural numbers this way. You could say, first of all, 0 is a natural number. So this could be empty here. N could be 0. If I don't have any hypotheses, then that's like a base case. It's an initial case where I just get it. And then the next one would be if n is a natural number, then successor of n is a natural number. So these two rules together describe the same information as the data type we just saw. When we defined the data type of natural numbers, that was basically the same thing in different notation. What was the difference? Well, okay, 0 was called 0, and successor was given, instead of these funny fraction things, it was given as a function, right? It looked like this. But this is more or less what this is saying. It takes natural numbers to natural numbers, so you might as well write it like this. So that's an example of an inductive generation. And the way that you need to understand these rules is that you say, okay, we are generating a type called n, and it's the least type, or the initial type, which is closed under these constructions. So it has a 0, and it's closed under successor. And it satisfies no equations except the ones it has to, but in this case, none. So what would be an example of a non-inductive type of natural numbers? Well, I could define, for instance, n infinity, and I would say it's the set of all numbers, but n also additionally an infinity, and then I define that the successor of infinity is infinity, whereas this is the normal successor. So this would be an example of a type which has a 0, it has the successor operation, but it's not inductive. And the reason that it's not inductive is that there is one too many. There is nothing that generates this element. It's just sitting there, and it wasn't generated by these rules. You'd never get to it using these rules. And in fact, because it's not inductive, it doesn't satisfy the principle of induction, right? You can't have induction on numbers where you also have infinity. So homework proved something ridiculous by assuming that you have induction for these numbers with infinity. So it's really meant, when you read the rules, what you want to read is just the stuff that's generated with these rules and nothing else. Yes?
But couldn't the infinite natural numbers be generated by some other sets of rules?
Yes, if there were some other rules, then of course it could be generated that way.
But then it still would be an inductive type.
Okay. So the question really is, so first of all, just so that we're in agreement, these two rules do not generate that type.
Yes.
And your question is there some other type? Are there some other rules that might generate an infinity?
Or yes, or in what meaning do you
Yeah.
are you using the word inductive?
Yes. So the answer to that is, well, there are lots of ways to explain inductive. I don't want to get into them too deeply, but one would be that an inductive type is an initial algebra for a functor. So that would be a category theoretic one. Another one would be a logical one, which would state that an inductive type has a corresponding induction principle. And it's the induction principle that you write down that gives its inductive nature. Now, to answer the question for n infinity is, no, this is not an inductive type. It's a co-inductive type. There is also something called co-induction, and that's final coalgebras for a functor, which has a co-induction principle and so on. And in fact, it's the co-inductive type for these operations. So there are programming languages that have co-inductive types. Haskell is one example. And so if in Haskell, if you define the natural numbers, you can actually define infinity, right? But Camel, you can't because it's inductive. So I hope that begins to answer the question. It's an important and broad question, but I can't really answer it in too much detail right now. Well, it has to do with the way Haskell is designed, that it has the infinity. You see, in principle, you could mix co-inductive data types with lazy evaluation, with eager evaluation. But it's a weird combination. If you're going to have lazy data types, you might as well have lazy evaluation. It fits better. But in principle, you don't have to put them together. Okay. So these are two slightly different things. Okay. In fact, the Booleans that we saw so far are also inductive, but they have very simple rules. So the Booleans we saw they just have two rules, which is false is a Boolean and true is a Boolean. These are also inductive rules. So if you just list like 7 things, you're going to have 7 basic axioms and nothing else. So that's also a special case. What else can we do inductively? Well, it turns out you can define all sorts of things inductively, not just data types. For instance, you can define a predicate. So let's have a look. So here are the rules that define when a number is even. So the way you read them is you say 0 is an even number. Yep. And if n is an even number, then the successor of n is also an even number. So for which numbers will you be able to establish that they fit this using these rules? For 0, for 2, for 4, 6, 8, and so on. So this is a definition of the predicate or the property of being even. So this is an inductive property. Many properties have this feature. Now, why do we care about this? Because Agda and programming in general is good when you do things recursively. But recursion is something that goes with induction. So whenever you have an inductive data type or an inductive predicate or an inductive relation, there will be the possibility of writing functions and proofs in a recursive way. And that will be an important tool to prove properties of things. Okay, now this is a little bit different from the thing above. Here, every constructor got its name. So there's a constructor called false, there's a constructor called true. But here we have 2 rules, and we don't have any names for them. So if I want to explain which rule I used, then I have to point with my finger, and that's not recorded on YouTube, so this is not good. So we want to give the rules names. Well, you could write them in several ways, but how about we write them like this? You could write them like this. You say the first rule, namely that even is 0, we call that even sub 0. We just made up a name. And the other one, we'll do it like this. We'll say if P is the reason or the proof or is the labeling of the fact that n is even, then I can record the fact that the successor of n is even by applying some constant even as sp. Okay? So, for instance, the fact that 4 is even is written here and it's justified here. This is simply the proof now. This tells me how to prove that 4 is even. These are super stupid examples. Later, they're not going to be so stupid, so you should still be paying attention. So, I can name inference rules in logic, and then I can use these names to write down proofs. Here, so how do I read this? Why is 4 even? First of all, 0 is even by the axiom called even sub 0. And then, by an application of the inference rule even SS to the fact that 0 is even, we get that 2 is even, and then we do it one more, and then we get the 4 is even. So, look at this, and look at that. There is no difference. There's no difference between these 2 cases. This is what Martin Löf said many years ago, and it's been resonating and has given lots and lots of insights. So, there is no difference between inductive generation of sets and proofs of propositions. Well, to be quite nitpicky, we can probably come up with some differences, but the idea is very important. The idea is, yes, there is a uniform way of treating both generating elements of a set using inductive rules and generating proofs of statements. So that way, we can do something super interesting. We can define the relation even just like we did in Agda. It's a data type. So today, we learn that the property of being even can be looked at as a special kind of data type, because what we do is we don't think anymore of this thing here as being either true or false. Don't think of even 0 as something that's true or false. Think of even 0 as the set of proofs. So think of it as a type whose elements are proofs that this is really the case. Then we can read this as follows. We are going to define a predicate even, which tells us when a number is even. So how does it work? It has two rules. I just copied them from above. There is one rule, one constructor called even z, which witnesses the fact that 0 is even. And there is another constructor which, from the fact that n is even, produces the fact that the double successor of n is even. And there is an implicit argument here, but we already know that by now, that we have to state that n is a natural number. You have to introduce the n. So we can type this in Agda. Okay, I can go back to Agda. Where is it? Here. 4 is even. So the way that you can program this in Agda is you say, okay, so let's do this in a non-silly way. Please prove that 4 is even. And what do I have? What are my options? Well, I can say, Agda, what do you want? And it says, your goal is to generate an element of even 4. Agda thinks this is a data type. I think this is a property. There is no difference. Agda thinks I need to generate an element of the data type. I think I need to generate a proof. There is no difference. So now I say, okay, how do I do this? I'm going to apply even SS. And I say, I don't know what I'm going to apply this. I'm not so sure, question mark. And Agda says, yeah, okay, you put in a hole. What do you want to do about this hole? You now have another hole. I say, I want to use even SS again. And then press Control Space. It says, nope. What? Why not? Oh, I didn't. Oh, yeah, it was Control. Thank you. It was Control Space. Control C, Control R means refine. So if I do this, then I give Agda the complete answer. But if I write just like this is not a complete answer. This is a complete answer which has a hole. This is a non-complete answer. If it's a non-complete answer and I just want to use, say, I want to use even SS to break this particular hole into something smaller, something simpler, then I have to press Control C, Control R, which stands for refine. And now Agda says, okay, I know how to use even SS, but now your goal is to prove that 0 is even. Okay? And so now I say, okay, even Z. Control C space. By the way, this is such an easy case that I can press Control C, Control A. Control C, Control A means autofill. And Agda will try to use the constructors to just fill the hole. And in simple cases, it succeeds, sometimes gives you a weird answer, but it works. I know everybody will love Control C, Control A, and this is your way to doom. You use Control C, Control A before you're ready, you will be sorry later, I guarantee. It's like using, I don't know, first order tactic in cock. You have no idea what happened. And it just worked, and you don't want that. Okay, so let me contrast what we just did with even with how you might expect to do it. So, how do we think of even? Wouldn't it be more natural to think of even as a map into false and true? And that's a totally valid opinion, and it's a good idea. So we could instead think of it as a map. What did we do? We think of it as, so this is like a map. I'll put B here. Did I put B here in the code? Yes, okay, just so that I can distinguish. So, and I said, no, it's like this. So if I define this set theoretically, what did I do? I mapped 0 to the set even ZZ, and I mapped the successor. Well, I'll write it like a true mathematician, okay? N plus 2 was mapped to even SS of even ZZ, something weird like that, where there are here n divided by 2 or something weird. But it was a set. The point is that it was a set. So why would anybody do this? Well, you would do this if you do this if you want just one bit of information. Here, you receive one bit of information, which is, does it hold? Is it true or is it false? Here, you don't receive one bit of information. You receive the reason for it being true. And this reason could be intricate. For instance, suppose we are discussing whether a given function has a 0. With one bit of information, I tell you, yes, it has a 0. But if I want to give you the reason that the function has a 0, I will give you an x at which it is 0. And I'll say the reason that this function has a 0 is because at this x, it's 0. So I give you the x, and I give you the proof that there it really is 0. That is a lot more informative, because now you know where the function is 0. It's a lot better than just saying, yeah, it's 0 somewhere. You find it, I don't care. Yeah? So this second one is more general. It gives more information than just one bit. Nevertheless, the first one is also useful, because that's a binary, this is what is called a Boolean predicate, and it can be quite useful. So yes, of course, we can define things this way, and here's a little exercise on how you do that. You can define mutually recursive functions in Agda. You first say, I'm going to define these two functions, and then you give a definition, and they call each other. I'm not going to go into details here because we're not in the kindergarten, so I hope you can understand this definition. It's not too mysterious. This is called a Boolean predicate, a Boolean function or something like that, when it maps into bool. It's less general than what we presented here, because there will be some relations that you cannot represent this way because they will be non-decidable relations. But this, when you can do it, can be quite useful. So let's just define this, let's record this, that a predicate is decidable if it can be represented like this by a Boolean function. That is to say, if I have some predicate P, which maps elements of A to reasons, so for each element, little x, P of x is the set of proofs that P holds. Think of it this way. It's represented by F if the following is true. F of x returns true if there is some proof that P of x holds, and it's false if P of x is empty. Whenever you can do that, you say that the predicate is decidable. So, this is something we might come back to, but I wanted to mention that this is an alternative which is not as general as what we're doing here with the viewing predicates as mapping into reasons why a thing is true. Okay, here are some further, let's look at some further examples of inductively defined predicates. So, you were going to tell me, so something like not 0. I'm going to define the Boolean predicate because everybody will understand it, but then you have to tell me the rules. So not 0 of n should be false, well, or should be, yeah, false if n is 0, and it should be true if n is not 0. Okay? Can we do this with inductively generated rules? How? So now I would like, instead of this, I would like to have something called not 0, which goes from numbers to set and is given by rules.
I have one rule without a proposition. I have just some p in the non-zero 0.
So, say again?
No, the other way.
The other way, yes. So what's the other way?
If it isn't true that n is 0, it is true.
Say again?
So not n is 0 is
What do I write above the line and what do I write below the line?
above the line nothing and below the line not n equals 0.
But it has to take the following form. It has to say
So
not 0.
postulate that 1 is not 0.
Postulate that 1 is not. I know how to postulate that 1 is not 0. I will say, well, I have to have some name here. Like, I don't know. I'll use stupid names right now. Foo, not 0. Successor of 0. Okay, so now my first rule, which is called foo, postulates that 1 is not 0. Okay, but well, okay, good. I'm not done. Am I done? I'm not done. Now what?
Given a non-zero integer.
So given that what? Given what? Given a natural number n, and given the fact that it's not 0, then what?
Its successor is also not 0.
Its successor, so bar np, not 0, successor of n. Okay, so this will allow us to prove that 1 is not 0. This then, because 1 is not 0, will allow us to prove that 2 is not 0, and then we can keep going. Yep?
Can you just simplify it by saying if n is a natural number, then successor of n is not 0?
Okay, so your suggestion is if I have a natural number n, then, what do I want to call this? As n, not 0, successor of n. Would that work? I think that would also work, right? So both would work. So you see that there are different ways of giving inductive rules for the same predicate. Let's see what I wrote here. So here I abused Agda notations just to teach you how to do it. So first of all, this is the rule that you suggested, okay? It's just a single rule. It's not two rules. We could also do this one, but the one that is in the code is this one. And let's read it. It says, we're going to define a predicate with a ridiculous name called not 0 without any spaces, and it's a postfix operator. That's the name. It goes from n to set. It has a single rule, which I call suc not 0. Successor not 0, without any spaces, of course. So this is just a name. And what does it say? Given a natural number n, which, by the way, I made implicit. And I'm doing that because I see that n will appear later. So Agda will be able to tell what it is. So given a natural number, here we have the fact that it's not 0. So if I wrote this without funny notation, it would be 0, this.
The problem is that if you give it n, then it proves that n plus 1 is not 0.
Okay, let's just, I'll get back to this in a moment. Let me just type. Without the funny notation, it's this. And I managed to clobber something. Here, like this. Okay, so okay, so this is how you'd write it. It's the same thing, it's just abusing the UTF-8 stuff. You had a question. The question was?
When you're proving like a property of an n plus 1 method.
You want me to prove that something is not 0? That what?
No, I'm saying like if you have some n,
Yes?
proving that n plus 1 is not 0. And like if you would want to prove that your n is not 0,
Okay.
does that do at all? Because
Let's see. Okay, so the question is, suppose, what happened here? Weird colors appeared. Suppose I want to, yes, no space. See now, it's complaining. It says there's no infix operator like that. Well, of course there isn't, because there is a postfix operator which doesn't have a space here. Okay, so the question is, how are we going to do this? because, well, there's just one thing we can possibly do, because there's only one of these things. So you could probably try to use this and say refine. And it's saying no. So let me just explain to everybody why this is happening. Okay. So I said, please use the constructor. There's nothing else I can do. There's just a single constructor. So if this one doesn't work, nothing is going to work, because it's the only constructor. So, but it doesn't work. Why doesn't it work? So let's explain. The goal is to prove that n plus 1 is not 0. But now, very importantly, n plus 1, how did we define plus? Let's go look. And by the way, in Agda, if you put yourself on a symbol or a name and you press alt period, alt dot, it goes to the definition of the thing. That is very good to know. Plus was defined in this way. And so Agda, when faced with n plus 1, will say, can I compute this n plus 1? And it'll say, well, how could I compute n plus 1? Does the first case help? Well, the first case is 0 plus something. But n plus 1 does not start with 0. It starts with n here. So I can't use this case. Can I use the second case? And it'll say, nope, you can't use the second case, because that would mean that on the left of the plus, you need successor of something, but here you don't have a successor of something. So if you try to compute n plus 1, none of these rules will apply. And the reason that none of these rules will apply is because n is general, and so it's not known which of the two cases applies, so it can't apply any argument. By the way, after you pressed alt period, if you want to go back to where you came from, it's alt comma, and nope, control. Oh, what? I forgot. Control C comma. Oh, I'm in the wrong buffer. Okay, there we go. Alt comma. I think in Visual Studio Code that's usually control minus. I think it tends to be. So there's some key binding. So the point is that Agda doesn't know how to apply this rule, because when it tries to see whether it could apply the rule, it says, well, in order to apply the rule, I need successor of something, and it doesn't see that n plus 1 will be a successor of something, because it can't do any computation steps. So we have now hit the reality of Agda. This is where real life begins. So far it was a fairy tale. And this is something that we need to learn how to use and why this is happening. Okay, so this is a very educational moment. Now, could anything be done? Yes, you can push this proof through, but with lots more work. It's not going to be just completely direct. Okay? What would happen if we use these rules? Well, let's think. No, you see, the problem is here. It doesn't see that n plus 1 is successor of something. So we would first have to prove a lemma that says that n plus 1 is equal to successor of something. Once we, right? So far, Agda doesn't even know that n plus 1 equals 1 plus n. By the way, we never proved that n plus 1 equals 1 plus n, so it doesn't know that fact. So we're facing several questions here. How to prove that n plus 1 equals successor of something? How to define equal? Well, that's also a good question, how to define equal. And so we can't solve this problem right now. We just don't know how to do this, okay? So thanks for the educational moment here, because you see that even though the definition is very nice, you still have to learn how to use it. It's not always easy to use it. It's now 3 o'clock. Oh, here's an easy one. This, it will succeed, of course. If I say 42 is not 0, now let's think about why this one works. Okay? So it says, what is the goal here? Well, the goal is to use 42 is not 0. But what is 42? 42 is actually the same thing as successor of 41. Because behind the scenes, Agda thinks of this 42 as 42 successors. Okay? It's just showing you the number 42. I could be, so when I say, please use my constructor, which was this one. When I say please use it, what it'll say, okay, in order to use this constructor, I need to know what n is, because I need to apply it to this n, but n is implicit. The user is not telling me what it is. So Agda wants to figure out what n is. So it looks at what it's doing, and it's trying to do 42 is not equal to 0. So it compares this thing with 42 is not 0, and it says, oh, I could take n to be 41. And it says, okay, n can be 41, because it's just by pattern matching it can tell that this is the case, and it'll succeed. If I try, so here, up here, n plus 1 didn't work. What if I try 41 plus 1? Will it work? Yes. What? Did precedences get me? Yes, you see, the precedences got me. Plus has precedence 6, whereas this not equal thing, because I didn't say what it was, has precedence 20. That's higher than 6. So 4, 5. 5 is lower than 6. There. Now I can write it like this. Now I'll have a problem with multiplication because that one is at 5. So, but in any case, what is the problem? Oh, no problem. Now it, okay, so but now it does work. Why did it work in this case but not in the other case? Because when it tried to figure out what this thing was, it did compute. Look, if I say, please compute 41 plus 1, it can use the second rule of plus. When you're trying to compute 41 plus 1, you know that 41 is successor of successor of successor, so it will use the second rule. And then it'll keep going. It'll compute all the way, right? Because it's a recursive function. So this is going to work. Admittedly, this is the sort of thing that we need to explain and practice and understand and so on, because this is something that I think is, from a user point of view, is a bit unfortunate, because you would want things to magically work anyhow. If you want things to work magically, then you shouldn't be using Agda. You should probably be using lean or something like that, where there is more magic installed. Okay, it's now past 3 o'clock. So where are we moving? Pick a place. 202? How big is 202? It's pretty big, right? Yeah, let's go to 202. Yes, so you want to try 0 is not 0, yeah? Yeah. Okay, so continuing from what we had here before, and also somebody asks, so actually somebody asks, let's try 0 is not equal to 0, okay, also. So the way to understand this is the predicate, let's look at this one because it's less confusing. Okay, so the predicate non-zero, it should definitely be the case that the intuitive meaning of non-zero n is the proofs that n is not 0. Okay, we want that first of all. That's what we want, because if we don't have that, then we define the wrong predicate. When you say not 0, that's what people mean. So the question is, does this definition and this deductive generation accomplish that? Okay, and the answer is yes, it does, because if you stick, just think of it this way: what happens if you stick in 0? So what are the elements of not 0? And I believe this was the question, was let's try to do that. Okay, so if we try to prove that 0 is not 0, let's use this one here. 0 is not 0. I have to write it exactly with this spacing, right? If I do this, it's just a name. If I do this, it will say this is not an infix operator. I have to write it like this, and then it'll be happy. And so what am I, oh, no, sorry, this one like this, but this one like this. That's the wrong not equal machine, not equal, 0. Okay, it says you're missing the definition. So if I forget the definition, it'll say, where is it? It'll color it, and I'll say, where is it? Okay, so we say, what is the goal here? And the goal, somehow ridiculously, it's displaying, okay, it's now displaying this with +1, but it wants me to prove, no, sorry, this is the, oh, never mind, I'm in the wrong place. I have to be in the whole, Control-C, comma. It says, your goal is to prove that 0 is not 0. And now, if I try to use this, it will say, nope, you can't use this because I don't see how you could achieve this. Because what it wants, it says, you have to provide an element of this type. But this successor doesn't land in that type. It lands in a different type. It lands in suc of n is not 0. So this is actually empty. Or to put it here, maybe it will be easier to explain, and I still need to plug in. There are too many wires. What is this wire here? I will apply the first rule of computer science. Surely you know the first rule of computer science. Okay. What is the first rule of computer science? Things work better when plugged in and turned on. It solves 80% of all problems in computer science. Okay, so why is this empty? It's empty because here are all the ways to generate elements. But I can't use this rule to generate an element of this, because whatever n I use, I will never get 0 here. I'll always get a successor. Yeah? Does that answer your question a little bit? Okay?
Totally.
Yeah, okay.
Misunderstood earlier.
Yeah. And does somebody wanted me to try 0, not 0? Are you happy? Who was it? It's okay? Okay. You can't use, I mean, you can try to do it, but it's empty, so you can't do it. Okay? What would be interesting, in fact, would be to show that this is empty. How do you prove that a type is empty? So, yes, so the way that you prove that a type is empty is like this. First, okay, so let me give you a ridiculous way of showing that a number is 0. One way of showing that a number is 0 is to show that it is less than or equal to 0. For numbers, natural numbers, of course. We're talking natural numbers starting with 0. So one way to show that the natural number is 0 is to show this. Okay. So one way to show that a set A is empty, you see, you can't really say it's not empty. All I can do in Agda is I can construct things. So the question is, what do I need to construct so that I will know that A is empty? And the answer is, you need to construct a function from A to the empty set. So if we define this, if we had a definition of this, which we can, then to show that a type is empty, you can do that by constructing a function from A to the empty set. Because now it definitely isn't the case that A has an element, because if I have such a function and there is an element here, then there would be an element here, but there isn't one. So that's how you prove that something is empty, by constructing something. Okay, we will see this in the future. Let's do a little more exercises with these predicates and stuff. So let's define equality. So is equality also inductive in nature? Can we? But let's think just about equality of the natural numbers. Next week, we're going to do equality for real, and it's going to be a big deal. But today, I would just like to practice giving inductive rules. So, can you give me rules that explain when two numbers are equal? And I will write down the first rule. 0 equals 0. Okay? Can you give me another rule? So, somebody should ask, somebody should suggest the following rule. X equals X, right? If you have X in natural numbers, then X equals X. This is a good rule. I really like this rule. And this is how we're going to do things next week. This is the best way to define equality, is to say, well, things are equal when they're equal. It's kind of ridiculous, but it works, but not now. So here's how you can define, with your bare hands, define equality of natural numbers. You say, the first case is that 0 equals 0. The second case is that if n equals m, then what?
The successor of n equals
Then the successor of n equals successor of n. And this can be used to define equality of natural numbers. It goes under the name that I will not explain now, but just to give you the buzzword, it's called observational equality. Okay, there is a reason why it's called that. I don't want to explain it now. But this is how you could define equality in an inductive way. Because now, in order to show the two numbers are equal, well, if you see that they're both successors, you just go and you decrease the problem by 1. And if they're both 0, then you're done. But, yes.
observational equality the difference between mathematics and computer science?
So that is a trick question. Definitely in certain parts of computer science, observational equality is the one that is the relevant equality to consider. And it has special features, and yeah. So let's try another one, but this time I will not give you an answer. You will tell me the answer. I want less than or equal. You will tell me what the cases are for less than or equal. What's the first case?
0 is less than or equal to 0.
Okay, try better than that. You don't have to say 0 is less than or equal to 0.
Yeah.
Okay, so that would be one case. But with this case, I should explain what n is, so I have to write here n. And then, of course, I should give this rule a name, so some name here. When I write the Agda code, I will give it a name because I have to give it a constructor, okay? But let's just focus on the rules right now. So, okay, is that it? Nope. Can you give me another one? So this will allow me, so the way you think about this is as follows. This allows me to prove, I'm trying to define x is less than or equal to y, okay? I now successfully consider the case when x is 0. What is the other case that x could be?
Every other number?
But every other number than 0 will have what form?
Successor.
So I should be thinking about successor of m here, because then there is some system to my method. I say, okay, I am recursing. I warned you that there will be recursion. I'm thinking of how I decompose the first argument. I'm saying, okay, it's 0 or successor. I know how to give a rule at 0. How do I give a rule when the first argument is a successor? What do I want?
Less than or equal to the successor of n?
Okay, so if the first argument is successor, then the second one presumably will be a successor. But what do I need to check?
That m is less than or equal to n?
Yep. And then, of course, you also have to say m is a number, n is a number. But these will be implicit arguments. So now I have rules for less than or equal. Yep. So for instance, how would you prove that 1 is less than 4? Well, you would say, oh, you have to write it differently. This is successor of 0 is less than successor of 3. I first use this rule here. You see how bad it is that if I don't have names for rules, then I have to say like this rule here, this is stupid, okay? But anyway, that rule there. So I have to check that 0 is less than 3, and then it's, well, this rule here, okay? And I'm done. Let's try this in Agda, shall we?
Question about equality.
Yes?
If we write just successor of n is equal to successor of n without any hypothesis, would that work?
So what would be your two rules?
0 is equal to 0 and successor of n is equal to successor of n.
Oh, by the way, here we also need n is a natural number, m is a natural, you need this stuff. So you're suggesting this one, right? This is much closer to this definition that, this is sort of halfway between the definition that we're going to do next week and what we're doing here when we're trying to think of decomposing equality into ever smaller parts. Here, you sort of do one step. You say, yeah, if it's a successor, then poof, now I'm done, right? So it's like splitting the previous case. You see, why even bother? If you have these two cases, you might as well just do n is a natural number, then n equals n. You don't really need you don't really need both of these. You might then, that's why I'm saying it's halfway to where we're going to be next week. We see again that you can define a relation or a predicate in several ways. And some of them will be more advantageous than others. Some of them may compute better. Some of them may generalize better. It really depends on what you're doing. And these are possibilities. For the one that you suggested, it works, but I would say it's halfway between two extremes. And so, I don't know what the advantage will be. So, it might have an advantage, for all I know. I don't know, I never thought about it. So let's define equality. So how would we define equality? I can't use the equal sign because Agda already uses the equal sign for definitions. So I'm going to use something else. And I'm going to use triple equal sign. But because triple equal sign is the general equality that we will do next week, I have here a subscript n. How did I type this? By the way, if you want to, okay, so I don't know how you do this in Visual Studio Code. But in Emacs, if you want to know how you type one of these things, you press, it's very easy, Control U, Control X, equal. Sure, why not? And then it gives you everything it knows about this argument, about this character, among other things, how to type it. Danielle gave you a pointer to some humongous page of everything you can type in Agda, where you can have fun looking for things. And Phil Wadler's notes are very nice, and they very politely tell you how he typed things so that you get to learn. I'm not so polite, so I just typed them. Okay, anyway, here are the rules. So the rules for equality are, first of all, now we take one number, another number, and then we produce the type of proofs that they are equal. The base case is 0 equals 0, which is here, and we have to name it. So I named it z equals z without any spaces. So this is just a symbol. And then the successor case, I called it this. And you see if m and n are numbers, and m is equal to n, then successor of m equals successor of n. Questions? Is it clear? This is the transcription. We could also transcribe your definition and all the other definitions. We could transcribe them because they were inductive. We would use this data business. You can read this at home. So how does one prove that 2 plus 2 equals 1 plus 3 in Agda? First, you come up with a silly name for your lemma because it would be too traditional to call this lemma 42. So you give yourself the name of the lemma that reminds you of what this lemma is about. Then you write down the lemma, which is that 2 plus 2, you see the type. And so what we told Agda is we're going to define a thing that has this name here, and it has this type here. So, ooh, wow. Does this? Now I have to try. Nah. No, sorry. Animals, maybe animals work. No, we're in some font that doesn't work. I really want to prove a pig lemma. I should fix my fonts. Anyway. How do you prove this? Well, you have to think about what it is that we're doing. You press Control-C, comma, and it says your goal is to prove that 4 equals 4. But 4 is a successor, so I know that I will use the successor case, which is kind of annoying to type. And so I say use the successor case, and I press Control-C, Control-R, which instructs Agda to use what I typed to reduce the goal to a simpler goal. And it says, yep, I can see that we could use the successor case to get where we want, but you have another goal. It's a sub-goal, and it's that 3 equals 3. So now you keep going, and you keep typing the same thing. Or you use black magic and you press Control-C, Control-A. Because it's so simple that Agda will say, hey, there's just one constructor I could use. Hey, there's just one constructor I could use. Hey, there's just one and then it'll do it. Okay, let's do something slightly less trivial. Let's prove that equality is reflexive. So I want to prove that equality is reflexive. How do you do this? You say, if I have a natural number n, I want to construct a proof that n equals n. And because I made this an implicit argument, I don't have to write anything here, and I just say question mark. And it says, yeah, how do you want to do this? And I say Control-C, Control-A. And it doesn't work, serves me right. Well, why is that? Because there are two cases to consider. I have one case for when n is 0, and I have another case for n is a successor. So I really want to split cases. So I will type n and split cases. And Agda says, okay, not only do you want to split on n, if you want to do that, then you need to also have n as an argument, but because it's implicit, we're going to put it in braces here. And by the way, I thought Agda was going to complain that I don't have n, but it didn't, it just inserted it in there. So it says, okay, you want n? It says, here is your n. I said, no, I want the cases. Control-C, Control-C again. And it says, that's what you wanted. Okay, 0. How are you going to do this? I press Control-C, comma. I need to show that 0 equals 0. Oh, but there is a case, that's one of the rules. 0 equals 0 is one of the rules. So I press this, Control-C space, and it's happy. I could also just say Control-C A. It knows. And here, let's see. Here I would use the successor case, because I have to prove, what is it I have to prove? I have to prove the successor of n equals successor of n. The successor case covers that. So I press Control-C R for refine. And I need to now prove that n equals n. How will I prove that n equals n? Recursively. I say recursive call on n. Because it's a smaller n, Agda will say it's okay. So you see that induction and recursion are intimately related. They're the same thing. A recursive call is like using an induction hypothesis on a smaller number. No, doesn't want this. And REFL, without the n, because it's implicit, right? I don't have to specify it. It'll just know. There we go. Transitivity, symmetry. I will leave these to study at home how this works. So the way you should do this is you should delete this, type it in, and say, how the hell did he do that? And then you say, let me see. I have 3 implicit arguments, so I don't have to mention those. But then I have an argument. This is a proof that k equals m. Okay, so I'm going to have a proof that k equals m. Let's call this proof p, and let's call the other one q. And I ask, what do I need to do? And it says, you need to prove that k equals n, and at your disposal you have q and p and n and m and k. N and m and k are implicit, so you can't actually mention them, but q and p are there for you to use. Often, people, instead of writing p and q, would write something like this. Because now, I know what the p and q stand for. See, this is the proof that k equals m, this is the proof. And I can say, how will I do this? Well, I need to split. I will split on what? And I could split on k or m and n. Which one will be best? Well, let's just blindly try one. K, sure. And now I need to prove that 0 equals n, but I have m equals n and 0 equals n and so on. So this is a good exercise at home. I'm not going to redo it now, because I can't do everything here, so I'll just leave you with this. So you can see that there will be, at the end, just 2 cases. So that's also something that's kind of interesting, that there are two cases. Why isn't there a case that is mixed? Well, because this one cannot be proved, because it can never happen, right? So it can never happen that m is 0, but then in the next step it's a successor. So Agda will figure out which cases cannot happen, and it will just not show them to you. Let's keep going here. So this was the definition of less than or equal. It's exactly what we said. So 0 is less than n. And if m is less than n, then successor of m is less than successor of n. We just typed it in as a data type. And again, now, you can prove things. So for instance, let's prove that n is less than the double successor of n. How would you do that? Well, you comment this stuff here, and you go and you say, how do I do this? And I say, well, if n, probably I need to consider what the cases are for n. So let me split on n. So split on n. Here I need to prove that 0 is less than 2, but that is one of the constructors. So what were the constructors called? The constructors were called 0 is less than any n, and the successor case, which will shave off one successor. So 0 is less than any n, use the fact. And it says, yep. And here, if I say, what do I need to do? It says, you need to prove the successor of something equals successor of something else. And I say, well, but I can get rid of one of the successors by using the rule that gets rid of one of the successors. And I say, what now? And you see that I have one fewer successor. At which point, I can use induction. I say, but now, this is just the induction hypothesis for a smaller n. So I can use the inductive call. So I use the inductive call, and it says, good, we're good. You will practice these things in the exercises, and then a lot more. Antisymmetry is much the same. So if you really want to get the feel for these, you should try to do some of these by yourself, okay? I don't think there is any point in watching me do 6 of these cases. I've now done 2 or 3. You should start trying to do them. Okay. Let's stop enough of these relations. Let's go back to some interesting inductive data types. So let's consider numbers again. So we define numbers in unary, right? Because we had 0 is a natural number, and then we had the successor. We had 0 and successor. And so if you want to have the number 42, it's going to be a lot of successors. It's not very efficient. Of course, it's better to use binary numbers. So how could we define binary numbers? Can we define binary numbers using inductive rules? What are the cases for generating numbers but using binary?
0 and 1.
0, okay, let me just write them like this. So 1 would be, okay, 0 is a binary number. 1 is a binary number. 2 is a binary, no. What now? It's a good start. We need infinitely more.
Given the binary number.
Given and a binary number.
0 and or.
Yeah, should we write zeros on the other side maybe? Or which side? I don't know how you're thinking.
I don't think it matters.
Okay.
Little and infinite.
So some way of writing 0 like this maybe. Later on we'll write it from this side, so let's write it from, in the code it's on this side, so let's write it on this side. You want to say something like this?
Yeah.
Okay, where
Also for n1.
this is like, so what would be the intuitive meaning of this? What number does this represent? If this,
Double of n.
the double of n, right? Is that what you, is that, I mean, I'm asking, is that what you had in mind? kind of, okay? Others think that you probably meant double, okay? Can somebody else suggest something else?
By adding 1 at the end, which is a double plus 1.
Okay, so the idea is that intuitively this should be something like 2n, and this should be 2n plus 1. Is it really the case that if I have a number in binary, suppose I have some number in binary, and if I add a 0 here, is that like multiplying by 2?
Yes.
Yes. And if I have a number in binary and I add a 1 here, is that like multiplying by 2 and adding 1?
Yes.
Yes. So this is this seems like a good way of doing it. Okay. Sorry, you had a comment?
Depends on your context a lot, how are you reading these numbers?
Right. So it depends on how I'm reading, but to explain where the idea comes from the fact that adding a digit on the right, either 0 or 1, corresponds to multiplication by 2 and multiplication by 1. There is also an even more naive way of saying this, which is binary numbers are just sequences of zeros and ones. So we just need to generate sequences of zeros and ones, and then we're done. So that's another way to say it. So how would you generate sequences of zeros and ones? Well, like this. Well, except that you could, instead of this, you could in principle start with an empty sequence. It's a bit weird because normally this does not represent a number, right? If you have an empty sequence of digits, normally you don't say that's a number. I mean, if you try to do that in school in the 4th grade, it doesn't end well. So, nevertheless, I think this is what Daniel put in the exercises, just so that you could practice getting rid of this undesirable sequence. Just for the purpose, we put it in for the purpose of having to take it out later. But this remark about the context was also valid. If I give you a sequence of natural numbers, of binary, of digits like this, okay, and I ask you which number is this, we have to understand the sequence correctly. So you're probably assuming the received wisdom of reading from left to right and the least significant bit being here. So in that case, that's going to be 1 plus 2 plus 8, because this is a 4, right? So it's going to be 11. But if you read it from the other side, if you read it like this, it would be 1 plus 4 plus 8, and then it would be 13. So that's so just once when we define the binary numbers, the data type, the only thing that we have at that point is a way of representing the numbers, but the data type itself does not tell us how we represented the numbers. In order to really know how they're represented, in what way do these binary numbers correspond to the usual numbers, we would need something else. For instance, we could have a translation from binary to the ordinary numbers and back, and then we would say, okay, if we understand the ordinary unary numbers correctly, then we know how to understand the binary numbers. Something needs to be done. Nevertheless, let's have a look at how the definition works. So here's the definition using the empty number as well, because in the exercises we want to have a slightly broken way of doing it. You could argue, that this way is also a little weird because it allows you to have arbitrarily many zeros at the beginning. So a particularly interesting question is how to inductively define natural numbers in binary so that every binary number has exactly one representation, no leading zeros. It's not so, it becomes an interesting question and is maybe not worth doing for most purposes. So here's how you could do it. You could say the empty sequence represents a binary number, and then if I have a binary number and I attach a 0, which I write here as an O, because otherwise Agda doesn't want the 0, because it thinks the 0 is the natural number. So if I attach an O here, that will be a binary number, and if I attach an I instead of an O1, that will be a number. So this is then 10 would be written like this. You would say start with the empty sequence, attach a 1, attach a 0, attach a 1, attach a 0. So this is the same as writing parentheses in there, but we don't have to. It's like this. But we don't have to, right? Because first I take the empty sequence, I attach a 1. Then I take the result, I attach an O. But you don't have to do that. Why? Because infix left here, because of this stuff here. Okay? Questions? This is just preparation for the exercises where you can then ask, how do you do the successor on binary numbers? How do you define addition on binary numbers? And then, of course, you discover some algorithm for binary addition and some algorithm for adding 1 to binary number, recursive. And you can define these functions. This is just to learn how to work with Agda. So there's one last thing that we want to cover, which is, let's also look at lists. Lists can be defined inductively in a similar way, but let's say we want lists of elements of A. So list A should be finite lists of elements of A. What are the cases? One case is the empty list. And the other case is when, if I have, let me write it as a rule. Well, so this one as a rule is just the empty list is a list. And this one, this one is so the next one is, how do you increase the list by one element? You say, if I have an element A in A, and I have some list L of elements in A, then I can form a new list. So I need some notation for forming a new list that takes this and that together, and it would be a little bit too confusing to write it like this. So I'll use the Haskell, I will use the OCaml notation, which uses a double colon like this. Then this one is a list in A. So the way you read this is, this is the list whose head is A, and its tail is L, where L is a list. So for instance, what you would normally write as list 1, 4, 5, using this notation you would write as 1, 4, 5, empty. And if you don't declare your associativity correctly, you will have to put in parentheses like this. So let's see the definition. Keep doing the wrong thing. Okay. Beware. This is not 2 colons. This is 2 colons. This is \2 colons, which is a single UTF character for 2 colons. Does there exist one for 3 colons? No. These 2 are together, and then there's this one is attached. Oh well. So this is a single character, which is the double colon character, which is \:::. So the 2 cases are, so let's think about this. I want to define lists, and I want to define lists of elements from set A. So here's a parameter, A, and then I will define a set. The first case is when I have a empty list. The second case is I give an element of A, so this was my little a. I give a list, and then I produce a list. But I don't have to name these elements because I don't need to name them, so I could write it without names. This is called cons. This operator is called cons. And there's built-in support for lists so that they are represented efficiently. So that's another pragma that you can use, and it'll look and say, yep, this fits my definition of lists, and it'll use them internally. So here's a list of elements: false, false, true. You can write it like this. Okay. What if we want, say, to generate a list of elements from 0 to n, or from n to 0? So we could do it like this, just as an exercise to reading definitions. Range, let's read the definition. Range takes a number n, and it returns a list. If the number is 0, it returns the empty list. If the number is a successor of n, it returns n, followed by a recursive range n call. So we can, for example, let's compute the range of 10. Range of 10 down here gives us the list of numbers from 9 to 0. Okay. This is going to be useful in the exercises. Local definitions. Let's try to define. Actually, let me just comment this out. Reverse, which turns a list around. So something which takes a bunch of elements. So this x's you read like a list whose elements are x1, x0. So x's in plural. X and s means plural of x. We want to reverse a list. How do we reverse a list? If you just try to do this by saying let's split on x's, then you say, how do you reverse the order of the empty list? Well, it's the empty list. But here, you're going to get stuck. How do you reverse a list that starts with x and then continues with some list of x's? You could say, I want to reverse the x's, and then I want to add x at the end, right? Reverse, but then add x at the end. But there's no operation for ending for doing that. You can't. So we would now need to define an auxiliary definition, auxiliary function that adds an element at the end of the list, but we're not going to do that. Instead, we're going to do what is very common when you have a recursive definition like this, which is we're going to build the result in steps, and then when we get to the base case, the result will be built. So let me show you how. You say, to reverse a list of x's, we're going to use an auxiliary function. So this is going to be a helper function called rev, and it will build the result by going through the list of x's. At the beginning, it hasn't built anything, so it starts with the empty list, and now the intention is that we are going to add elements of x to this empty list in such a way that we will get the reversed list. So when you want to have a local definition, I want to have a helper function with a local definition, the way that you do this is you say afterwards, so this is super weird. In Agda, when you have a local definition, you can have it in front, like in OCaml, let x equal n, but you can also have, you use something, and then you say where, and then you define it afterwards. Mathematicians like to do that. They like to use something and then say where, blah, blah, blah. And so Agda allows that. Where, and now we have to define rev. Okay? So rev is going to take a list of a's and another list of a's, and will return a list of a's. And the way that we do this, if you have seen this exercise in, oh, by the way, because I have a here, now I need to mention a. So I put a here so that it is visible, like this. It's an implicit argument, but for the definition I need it. Okay, so it has partial result, which is sometimes called the accumulator, and then it has a list of things, the x's. And now I say, okay, how I do this? I split cases. If I already processed all the elements, then the accumulator holds the answer. So I return the accumulator. Otherwise, if I have a list, what do? I will call recursively on the rest and I will improve my solution. I will say the accumulator should receive x. And if you think about it, how this is going to work, the accumulator will start empty. Then I will add the first element to it. Then I will add the second element to it. Then I will add the third element to it. So the elements will be added in such a way that they will reverse the order.
You just became pieces.
Say again?
You just became pieces.
I became?
Pieces.
The CS, I think. The CS is shit.
You popped it from one stack and you pushed to another.
Ah, yeah, okay. And this is the same definition as here below, just with different names for variables. Let's try to compute. Reverse range 10. And now it's in the correct order. Right? Reverse, range 10, remember, was in this order. Reverse range 10. Okay. You will want the wheres in some of the exercises. What is this business here? You don't have to use the local definition, of course. I could pull out this definition of rev and just put it in front of reverse, like this. Make it global, okay? But it's generally good programming practice to keep definitions local when their nature is local. So if you're going to use something just in one place, don't make it available everywhere. Because sooner or later, some other idiot is going to use it, okay? So don't let them do that. That other idiot is going to be you, by the way, just 3 weeks later. Yeah. Okay, we're done for today. Tomorrow, we shall see what happens. Come to the exercises.